Okay, so for completeness sake, let's just quickly go through what we did in the previous chapter. We set out to generate, at the end, we set out to generate text using the model that we had built. So let's put the model here because we're going to need it. So we have our layer normalization module here. The way we're going to normalize subtracting the mean. We're going to subtract the mean and the variance. We're going to subtract the mean and then divide by the square root of the variance like we did previously using these apps, just to make sure we don't divide by zero. Then we have this GELU, the GELU activation with our formula here. Remember our GELU using this module, and it's going to be calculated by this approximate formula here. Perfect. Then we have our feed forward. That is our layer, which is the linear layer. We have the GELU part, and then we have a linear layer as well. And there's going to be an explosion in dimension times 4, and then here we reduce our dimension back. We reduce our dimension as our output, which is the embedding dimension, right? And then we have our multi-head attention, which calculates our QKV matrices, and it does masking. So this is our masked multi-head attention. That's what we are going to have there. We're going to choose our number of heads that we're going to use, all of that stuff. And at the end, it will calculate our attention weights, which will then be converted to context weights using the attention weights times the value vectors. You can go back to the chapters to see how we did this. So now we have our context vectors, and then we'll have our transformer block. Our transformer block will make use of our multi-head attention, feed forward, normalization layers, two of them, and our dropout. To have our dropout in different places. This one here is for the shortcut. So then it will just first first it creates a shortcut, normalizes what is coming in, gets it into the attention, will then drop out and then add the shortcut to the output of that first part. And then it will then create another shortcut, normalize what is coming in, and put it in the feed forward, drop out, and then add the shortcut, and then it will return the result. Easy, straightforward, like we did. Then we wrapped everything in the GPT model. So this is our model actually, which wraps everything, which is our after tokenization, it then gets into our token embeddings, positional embeddings, and then drop out. So the forward is actually the one that is showing us the stages. Here we're just instantiating them. So what happens is we have a bed size. We first get our token embeddings, we create our positional embeddings, and we add the two. Then we apply dropout at the embeddings layer. Then the output gets into our TRF blocks where it will do all the multi-head attention and all of those things. And then we have our final normalization out of the TRF blocks. Then we have an output head, which we have our logits. The logits can be converted to probabilities for each next token that would have been predicted, and we choose the one that is the maximum. That is the simplest one, the greedy decoding. We choose the one that is the maximum probability. That's it. And this is our GPT config. We reduced our context length to 256 just for it to be easy to run this in Google Colab, because the GPUs that I have there will just be, if you go to connect to a runtime, change runtime type. These are the GPUs that I have access to. So for it to train, to pre-train, just reduce the context length. But the original is 1024. And later, when we're doing loading of weights, we are going to change it back to 1024 because the weights are already there. We don't need to train. So that's just it. We put our model, so we instantiate our model object, and then we put it into evaluation so that we disable things like dropout, because we are just doing inference for now. We create this function that generates text. You can read what the function does or use this AI feature You can use it to explain code, and Google Colab will explain this block here. But pretty much we're just generating text using our model. And when we have our logits, we convert them to we use softmax to convert them to probabilities. We find the argument that is the highest probability, and that is our index of the next token. And we just concatenate it to the indexes that we have had of generated tokens in the previous runs. That's what we have here. And now that we have our index of the next token, we can use that index or the indexes that we have to generate text. So here we just say, excuse me. Here we just use text to token IDs. This is for tokenization. We're going to use the tokenizer from tick token, and we allow special characters so that we know that there's the end of text, and that's it. So this is the end of coding. And then we also want to convert the token IDs to text, because once we generate these token IDs, we want to know what the actual text is. So that's what we are just doing here in this function here. So now let's start. Every effort moves you. We get the tokenizer that was used for GPT-2, and we generate text. We say, what model are we going to use? It is our GPT model that we have. And then our IDX, we're just going to say text to token IDs. We're going to tokenize our start token, start context using our tokenizer. So that now we have our token IDs. These token IDs are then here, the token IDs, and we generate simple text. As you can see, when we're generating simple text, when we're getting these, we are actually getting token IDs. So we use our token IDs to text so that it converts back our token IDs to our words, to normal words, like we're seeing here. So that when it does the runs, it's going to do multiple runs, multiple iterations using this model when it's generating simple text. So if we go to generate simple text, we'll say what max new tokens are we going to generate? So how many iterations? So every effort moves you. We can say we want 10 new tokens. So it adds tokens on top of that so that we can get if we want max 10 new tokens, add 10 new tokens. Here we just said we want we said we want 10 new tokens. So it will then calculate the tokens, then iterating using our model. Every effort moves you one. That's a new token, and then step. That's another run. Forward. That's another run, and all of that. So now let's see what it has generated. So here you see every effort moves you. That is our starting context. Then it starts writing gibberish. Why? Because this model has not been trained yet, and that is the I, that is the crux of this chapter. The crux of this chapter is how do we make the model generate coherent text? And someone would then ask, but what do we mean by coherent? And that's a good question. We need to define what coherent means. And because we're using large language models, which are deep neural networks, that definition of coherency needs to be mathematical. To our words that I'm speaking right now, they're coherent because we understand language, we understand words. But large language models are deep neural networks, they only understand numbers. So, which means coherency needs to be in numerical format. So, that's where we are going to define something called a loss metric. As you can see here, we're going to define loss. These are the matrices that we are going to use: cross entropy and perplexity, and we're going to use them in the next video. But essentially, we're going to say if we calculate this loss metric and it is a high loss metric, it means that our text is not yet coherent. And we're going to see how that happens. If we are going to train the model such that it reduces the loss metric. We know that by reducing the loss metric, it is creating coherent text. And then we'll test it in words. Can we read the words actually as humans? Does it make sense that as the loss is going down, the words are becoming more coherent? We're going to see that in the next video. So let's stay tuned for the next video, because now we're introducing new concepts.